Okay, in this video we're going to take a look at using Iterator and Intersect in order to have particles be able to look around in certain directions and create some samples on things that are in front of them. And we're going to go ahead and use a little axis helper here in the beginning to act as our particle. And then we're just going to detect intersect hits on this box. This is all going to be really easy, of course. The problem or the challenge and difficulty is going to come when we start to do multiple samples, because what we really want is not just one sample directly in front of a particle, but kind of a weighted sampling where it samples quite a bit kind of in front of it and then somewhat around it, as well as the ability to control that, how many samples it generates where. And so one of the ways we're going to do this is we're actually going to create a random vector based on a circular pattern with the x and the y components. And then what we're going to do is, because we want that to be based on the particle's alignment, we're going to need a method to transform that x, y kind of circular sample and transform that into the alignment space or the particle space that we've got here. So we're going to end up writing a little script operator to do that. Okay, so let's zero this guy out and just kind of rough in what we're going to need. So let's get some groups to work with. We get the colors, black box, and we know that we're going to need a couple nodes. We'll need one node to be this box, which is going to be our intersection test, and the other node for now is going to be the point helper. And of course, setting up an intersect is as simple as dropping this in here. The node's going to determine what it intersects with. We're going to want the speed as ray length to be turned on so that it will detect intersections all the way along its ray length. And it's one of the things we're going to need to do also is see what kind of world scale we are dealing with. So we'll just use the line tool, our favorite, and click here and drag out here. And the thing about line tool is as you move that point around, it's going to tell you in the status bar what kind of distances you're looking at. So if we've got 130 units here, setting this to 200 will give us more than enough kind of ray length to use. And then, of course, when it detects a hit, we want to create a particle. So we'll go ahead and create a green particle, 1 per call. We're going to set its lifespan as 0 because we only want this particle to be alive during this current time sample. And so we don't need that either. Okay, so the direction, for now, we'll just set up a simple example. We will use the y-axis from this helper. So let's use get direction to take an alignment, break out and get its y direction. And then from the position, we'll use the position of that point node. And remember, we're using this point helper as a particle. We're treating it as a particle, and then we're going to apply this to particles here in a little bit. Okay, and so then we'll go ahead and say wherever there's a hit, I want to turn on position on, and wherever that position is from the intersect is going to control where it is born. So now, as we rotate this guy around, we can see obviously that the y-axis, or the y direction of this alignment helper, or this particle, as it were, is controlling where it points and where it samples. And the thing here, of course, is that I guess we could have chosen some better colors, but it's just we'll make our axis helper kind of a gray. We actually want particles to not detect directly in front of them. That's way too easy. If this particle is a ship and it's flying through space, then obviously directly in front's not going to be enough. It's got to be kind of a circular sample, and not only that, but it will actually have to be enough samples to cover the entire shape of that ship. And we'll take a look at that in a following video. It's pretty easy. What you do is you birth surface samples on the ship, and then from each of those surface samples you do an intersect. And in that case you can actually either intersect directly in front if you have enough samples on the ship, or you can actually add some iteration and some slight direction change to each of those surface samples. Okay, so we got our intersect set up. We got this. Okay, now let's talk about what the other things that we want to do. We want to set up the multiple samples here. And what we want to do is whichever direction a particle is facing, based on its, in this case, its y-axis, whichever direction it's facing, we actually want to generate a whole bunch of randomized samples. And in this case, we're going to use a circular kind of pattern. And then we're going to generate random directions, and then what we're going to do is generate those random samples around in a circle, and then we're going to have to transform those samples through the matrix or the alignment of our particle. And to do that, we're going to need a script operator that we're going to go ahead and write here in a second. So first thing, let's go ahead and do this. Let's generate our random circular pattern. We're going to generate between 0 and 360 to cover the entire circular kind of range. Randomize, we'll set it to per call. And then we're going to need an expression helper. And since edit on the fly is turned off, we get an error right away. We'll just set that to 1 so it'll stop with the errors. Then we're going to need one input. Let's just go ahead and use A, nice and generic. And our output, we're actually going to create a vector. We'll just call that vector circle. And what we're going to do is we're going to connect that random to there. So we're going to have a random value between 0 and 360, and we're going to create a vector. And we want this vector to be projected through y space, so the y component will be 1. And here from the front view, let's go ahead and get a circle in there. So this is the front view. So our axes here, x goes this way, z points up. We're going to actually use this 0 to 360 and say, okay, well the x component is going to be the cosine of this random number, and the y, or in this case the z component, since this is the z-axis, is going to be the sine component of that random number. So we'll just go ahead and create a vector here. We're going to do a cosine of value a, and then remember our y component is going to be 1 because we want that always to be going forward, and then our sine of a for the z component. And let's actually go ahead and just kind of reconnect this so we can see what that's doing. Let's turn on, let's set our random to per call, and then we will go ahead and throw an iterator in here to generate a whole bunch of samples. Iterator right there. Iterate, let's do your count, let's get it up there a little bit. Okay. Now, unfortunately, well, there's our circle. It's just really small because this is the, let's go ahead and measure this. You'll notice there in the status bar that that is about 1 there. So it is generating around x and z, and it takes that 0 to 360 value and creates a vector out of it. Here we'll show you if you do 0 to 180 roughly, obviously we get a half arc. So that'll come in handy if you're dealing with characters who are standing on a ground plane and don't actually have to look down at all. Okay, so that's all good, but we actually want to control the some distance in this. So let's do this. Oh, you know what? Let's not. We're going to get into that in just a second, because remember what we're doing here is we're taking our y-axis of our particle, taking our y-axis, and then we're generating some extra randomized values in a circle around that y-axis in order to kind of look out in those different directions. So what we're going to need now is something that's going to take this this vector that's created by the circle and actually transform it through the matrix of our particle, the alignment. So let's do this. Let's open up our editor. Let's find a script that's going to be fairly close to what we want. We're going to use one called alignment math. And so the first thing we're going to do is save this as a new name so that we don't screw up like we usually do and overwrite our scripts. So we're going to call this vector transform. And next thing is we'll go ahead and replace all instances of the script name with a simple replace. We'll call it vector transform. So find next, replace, place, name, the registration, and then finally the top name. So I can't find any more. That means we're done. Then we know we're going to need a new class ID. So let's create one of those. Okay, and so then next up, now this, what was alignment math, let's take a quick look at that so we can see what it was doing. Alignment math took two alignments and allows you to add, subtract in certain directions, inverse, average, multiply. And it will actually output a new alignment or a difference percentage between the two alignments. We're actually going to modify this to what we want now. What we do not need is we don't need that matrix func, nor do we, I don't think we need the result either. So we're just gonna, but we do need a variable here, so we're gonna put no vars in. Our parameters, we're not gonna be using that anymore from this previous script, so we'll just take all that stuff out. We'll leave it as a helper. And then here's where we're going to start to modify stuff. One of our inputs is going to be a 0.3, because remember we're transforming a vector through a matrix. So this, we'll just call this vector. And we do want this to be required, so we're going to say it's needed. And then we're also going to need an alignment, which is going to be our matrix that we're going to transform through. We'll leave that named alignment, and also this is going to be needed. So we'll do that. Okay, then the outputs is actually going to be a new vector, a new 0.3. So let's change this. And for now, until we can come up with a better name, we'll just call it new vector. And remember, actually what we're going to end up doing is creating a new vector and not just a new direction. That'll become important later. Okay, so here in the juicy guts of the script, we've got the TP calculate. If the out ID is greater than or equal to 1, meaning it actually wants one of these outputs, it wants something is calling one of my outputs, then let's make sure that both, and in this case we've got these input changed. I'm not sure if we're going to want to detect whether these are changed or not, so we'll just leave them as they are and modify them if they somehow blow up. We're going to want to change what our get in value is. Our get in value 0, remember, references our first input, our 0.3. So we're just going to call this vec, and then our second input, number 1, we're just going to call that align. And then we do a little check here that says if, and this is supposed to be now vec, if vec is not undefined and align is not undefined, then go ahead and create whatever math result that we need. And in our case, what we need is we're going to create something called result equals vec times align. And what that does is it's going to multiply the vector against the alignment and put the vector in the alignment space. Case TP out ID, we'll leave some of this structure in here in case we need it. We don't need all this mess at the bottom. That's from the previous script. Nor do we need the case matrix funct of, which was part of the alignment math to help us determine which function we wanted. But in this case, we'll just go ahead and output the result. And we'll go ahead and update and save that, and then we will go ahead and look for our script here. It's going to be under helpers. M3D was our category, and it is vector transform. Okay, so let's see if we can create an easy way for us to evaluate this. Let's do this. First, I guess what we'll do is we'll take the y direction as the vector, and we'll take the nodes, remember this point helpers alignment as direction that we're going to modify it through. Actually, you know what? Let's not take that vector, because we want to actually create a new vector that we're going to be modifying. And go ahead and take this guy and say, leave it at per call. Wherever it gets a call, wherever it receives a new input, it's going to create a new position or a new particle. Okay, so what we've got right now is we've got a vector here that's 0, 0, 0. We've got an alignment based on this point helper's y alignment. And what it's doing is, right now, it's just creating that particle at 0, 0, 0. Because we actually need some vector values here. Let's actually go ahead and move this forward a little bit. Okay, and so now we can see that as we rotate this alignment, remember this direction's not being used right now. We're taking the alignment of the node and we are using this vector here, which goes out 55 units in y, and we are kind of reorienting where this vector is pointing, because we're multiplying it by the alignment. One of the things that we're seeing here, though, is that we can move our helper around, and it's really only the alignment that matters. So I think what we want to do is go ahead and add a position control so that we can actually also update this later. This is kind of going beyond. For this particular script, all we need is to actually transform the direction, but you can see cases where you would want to also use a position, incorporate the position for how you displace that vector. So we'll go ahead and we're going to add a new input. TP in out. Let's add this will be a 0.3. This is a position input. And actually we're not going to make this one required. This will be kind of an optional. And just keep our notes in here as to what its input is. And so what we're going to do then is say, well, we're going to come up with a case where if the position is attached, then we also want to kind of base this vector displacement on that position and have it orient and start from whatever position we've got coming in. So let's do this. So vector is this. We'll say, we'll add another if here. We'll say if TP in out input connected number 2, then what we'll do is we will say if our input's connected, then we're going to create a new variable here called position equals TP in out get in value 2. We want to access that position and assign it to this position variable. And then what we're going to do is if it is connected, then our result is actually going to be different than what we've got right now. Let's grab that. Our position is this, and then our result is going to be, let's say, our position plus that. And if it is not connected, if the position is not connected, then the result is just going to be that direction that we had. Okay, then our output test here can be the same. We don't need to update this. Remember, this is just kind of set up in case there's multiple out IDs. Okay, let's go ahead and turn on our listener and make sure that when we evaluate, everything's okay still. Let's save and update. And we'll go ahead and recreate it just to be clean. Now we get our position input. So our vector direction that we're going to be modifying, the alignment space that we're going to be translating that vector into, and then the position of how it's going to be manipulated. or the starting position. Okay, let's see what we get here. Okay, now as we move our helper around, our node helper, its position is kind of acting as the starting origin for our displacement of our vector. You can see as we, let's get that roughly like this, as we change this vector, we add some more in the x direction, or the negative x direction, or the positive z, negative z. We can see that particle being shifted in space there. Go ahead and leave that at 0 for the moment. Okay, so we can see that we get this, this vector completely kind of projected through this other alignment space. That's working fine. Let's go ahead and start to integrate the random circle stuff into this. Remember, our circle here is generating a vector. It's kind of hard to see because it's so small, but as we zoom in, now we can see that that circle is getting updated and it kind of maintains its alignment. It's a lot like p-attach or lock bond if you're from p-flow. Okay, so we actually want to now have the intersect be shooting rays based on, in this case, our y direction, or whatever direction that we want, and add some of this circular random in here. But this circular random is going to need a little bit more work. Right now it's kind of a constant distance from here. We're actually going to set this up so it's kind of got different sampling, more toward the middle and fewer toward the outside edge. Okay, so what we're going to do is we'll turn on our node here. We don't need that get direction anymore. Let's get rid of that. Let's turn on our own node because we're going to start to detect the intersections. We're going to want our particle, green particle, to be created when there's an intersection again. So let's turn that part, hit and position on. Okay, and then we're going to take our direction and put our direction here into the intersect. So remember, we've got our node controlling its alignments, controlling how this vector is being transformed. Something that we're going to have to do here, though, is disconnect this position. We actually don't want the position now to be included since we're dealing with the direction. You can leave it on and find out why. Okay, but here now, as we kind of rotate our helper node around, you can see that it is, actually let's get it closer to the circle. We can see those samples being kind of skewed and distorted as those rays are being generated and sent out there. So right now all it's doing is, remember, our vector direction that we're creating is kind of that random circular where it's in the x and z plane and always a 1 and y, so that it always does go forward. Oops, and I just deleted that. That's you gotta love that with TP in the. Can we back up twice, 3 times, 4 times? Nope. Okay. Yeah, leaving your mouse inside the expression operator is kind of a hazard. Okay, so that's back. That's great. What we actually want to do is randomize this, though. So we're going to actually introduce a new input. We'll call it rand. And rand is going to be a random value between 0 and 1. We'll see why here in a second. And this will be per call also. So we're going to multiply our x component, and we will multiply our y or z component between that 0 and 1 value. And now you can see that we get a whole bunch of samples kind of distributed around this way. Okay, that's all good, but what if we want our samples to kind of be more centered on the object and not so many on the outside. Right now it's a completely random kind of sampling out of there. Let's actually pull this away a little bit too. What we'll do for that is we'll grab our weighted random black box, which is just a kind of an easy little lookup here. What it does is it says generate a random number. We're going to set this per call. So it generates a random number between 0 and 100. That 0 and 100 gets fed into the value to time value. So that value gets evaluated if the random number is between 0 and 100, which matches that. If it's between 0 and 100, it translates it into a time value between 0 and 80. And that 0 to 80 time value comes out here into this curve, which has a curve on it. Oops. If I can grab that track view. And unfortunately, TP always accesses the selected track view. We'll see if we can't change that at some point. But down here, here's our helper curve. So what we'll do is we'll actually, you can see as we generate random between 0 and 100, it looks up between 0 and 80, and it queries this curve and says, hey, at whatever time between 0 and 80, what's your value? So the curve, of course, from 0 to 80, if it's anywhere, if the random number is anywhere in here, it's going to be pretty low until only a few of the numbers are going to be reaching up in the high area. So this is just kind of a weighted random. You can weight where you want those values to be, and we'll see how that happens right now. Actually, I'm going to disconnect the purely random, hook up our weighted random, and now as we adjust this, we can see that we get control over our curve and distribution of points. Let's actually add a few more toward the outside edge, but we'll go ahead and pull some of these points and samples down into the middle. So this just gives us a little bit of artistic control to modify how this occurs. Let's get some more points in there. Okay, now one of the problems is that we've left kind of a hole in the middle. And that's because our little curve value does not actually reach 0. So we'll do that, or we'll come a little bit closer. Actually, we'll spread those out. So that should be pretty good like that. Okay, so as we rotate this around now, we're getting this kind of sampling that's spread out like this. So we'll be able to set this up so that as particles are moving through space, either flying, walking, or whatever, they're able to kind of see out there in certain directions and determine, hey, what's in front of me or what's near me? Am I about to hit something? How far away is it? Is there a way out of here? Things like that. And so you can see as we scrub forward in time too, because our lifespan is 0, we get new samples every frame. Or if we were to set this to per half frame, we would actually get new samples every half frame, even though we only see them per frame. Okay, so this is just kind of one first step here. Remember, we've built a script operator to transform a vector through an alignment matrix. And we have particles now doing an intersect with kind of a randomized pattern looking out in a certain direction. Let's see. Remember, we can also do this. We can say, hey, if I'm standing on land, you might only want it from 0 to 180, that kind of circular random. And remember that what's happening here is we're taking the alignment, basically the y direction of a particle, and we are kind of adding a random value, in this case a half circle, with some different kind of distance away from the origin in order to kind of sample in a randomized pattern around there. Let's go ahead and actually get a particle in here, and we'll see what we get. In this case, why don't we draw a blue particle, and we'll go ahead and draw him right there. And in this case, we're going to set this up a little bit differently. Actually, for starters, we'll go ahead and save this file. We will save it as, I believe we are in advanced area. For now, we'll call it, let's see. We'll call it Iterator and Intersect, version 1. And of course it'll have a prefix on it based on where it is in the chapter. Okay, so we've saved this out, so now we're going to modify this file. Our previous setup is safe. And so we'll say blue particles, wherever you are, blue, at birth. In this particular case, we'll just test at birth. Don't need that. We'll keep our weighted random here. And remember, this is our helper node, and this is what we're mostly going to replace. We're going to use the particle, automatically derive the position when we connect that to particle. You can probably hear those birds outside. They are excited. And the other thing we need is the particle alignment. We can just connect the particle directly into the alignment because this input is an alignment type. We see that there in parentheses. Okay, let's see what we get. And we get nothing. That's awesome. That's always a great way to start a test. Let's go to the side view here, and because I suspect that our particle alignment is may not be what we think it is. Actually, here's a better way to do this. We can create a circle or a sphere. Set our node to be the sphere. Tell intersect to be two-sided. And that is awfully bright, so let's give you that. Can hardly see our blue particle, so let's change his color a little bit. There it is, hiding by the TP icon. Okay, so something is obviously wrong. I love it when that happens. It could be that our iterator needs to be activated by our particle, and that is the case. Iterator's kind of funny like that. When particles are involved, you may have to control the on input either by connecting a specific event like a particle age, or connecting the particle itself to the iterator. When something's not working, definitely try that. So we'll just do it right now. Let's not do the particle age thing, because we really do want this to sample at all times. Okay, so from the top view, here we get our particle looking like this. And remember, our particle only lives 24 frames, so let's change that. Let's make it 240. But let's also do this. Let's tell our particle to spin at birth, and we will see that it updates and looks around at those different directions. Spin time, we'll put it to 1. Let's do a user-defined axis, not Z, but actually, yeah, Z. We want it to kind of just kind of circle around the Z axis. So we can see that it ends up looking around all those different directions. Let's actually modify this a little bit and get it to do something a little more fun. Okay, so we've got a particle is now able to look around and detect things. We're going to want to set up a scene or a case where we can actually use that information. This information is useful in a lot of different ways, like I said, for either detecting obstacles in front of you, or just being able to kind of look around in certain areas, looking for ways out of something. So if there is not a hit in a certain direction, that might tell that particle, hey, I should go that way, while still looking for my ultimate goal, whatever that is. Okay, I'm trying to think. Anything else on this? I think that's going to be it. So we'll go ahead and save this out as... Remember, the video is going to be part 1, so this will be version 1 using a particle. Okay, so let's move on.